Hello, everyone, and welcome to Ask the Experts. I'm Tim Messagey, and I'm joined by Sharad Chole, who is the co-founder and chief scientist at Expedera. Welcome, Sharad.
Thank you, Tim. Thanks for having me here. Hello, everybody.
Great. Hey, today we're going to be talking about AI. So let me begin with this question. Sharad, can you give us some context about where Expedera fits into the AI ecosystem?
Tim, Expedera is a neural network IP provider. Basically, we call it an NPU for a shorthand. NPU stands for Neural Processing Unit. It's a similar terminology as CPU or GPU. Uh, we we've been pretty much focused on neural network inference on the edge devices. And Expedera was founded like in 2018 in Silicon Valley. And since then, we are at a third generation of our architecture. Um, our customers have already taped out more than 10 million devices. And what we focus on is how to enable a next generation of workloads with low power, very limited bandwidth, and significantly lower cost.
Thank you, Sharad. So if we take a look at today's, kind of state-of-the-art AI training, you're talking about trillion plus parameters. How big are the inference models that are coming out of that process, and what are the implications for trying to deploy those models beyond the data center on edge devices?
Tim, I think this is like a two-part question. Let me try to address the first part. So uh, when the neural network started picking up steam on edge devices, the most of the networks that we saw was were pretty much focused on object detections, and the sizes that we are seeing was in few hundred million parameters. But as Gen AI started coming into the picture, uh, we suddenly see humongous increase in the model sizes. So, like, let's start with stable diffusion, for example, right? Like, we certainly have model which is around 1 billion parameters. And then stable diffusion XL is around 5 to 6 billion parameters. And the trend continues towards video diffusion models. On the other hand, LLM pretty much took this idea of like we can have large models and just extend it to few hundred billion parameters. That's pretty amazing. Like if you think about it, like storing just the model parameters right now for the Llama 3.2 largest model, it requires 1.6 terabyte of data just storing the model parameter, and that is pretty challenging. Um, when we are looking into like I'm trying to address the second part. When we are looking into taking these models and trying to deploy them on the edge, the biggest concern is how do we manage the memory for storing the model? We can't just have them like stored on the SSDs. We do have to have them in the DRAM and to be able to access them efficiently. And a lot of things has to be optimized to be able to like enable the edge inference on these models. For example, we are looking into how the model weights can be quantized. Typical quantization does not always get accuracy, so we might end up using group quantization. We also might need to do a low bit precision quantization, like for stable diffusion, you can go as low as a 6 bit or slightly lower than that, while still maintaining the accuracy. There have been effort in academia for LLMs to go to 1 or 2 bit. But to be able to like maintain robust accuracy, there have been palette-based quantizations or more refined way of restructuring the model, where we are not really training the model from scratch, but using a larger model to train the smaller model. And this is called as knowledge distillation, or in a way, it's a teacher-student way of like training a smaller model as a student and a larger model being teacher. And this results in better alignment of the smaller model with the resulting context. Um, One thing I might want to point out here is like why we are going towards larger model. And this is very interesting to me. It's because of scaling laws. So there is a point at which the models start exhibiting interesting um, capabilities. Like it's not just predicting the next token in from based on what is similarity in the corpus, but it's actually understanding your question and context, and you can give it more complex question. One example that I can give you is like if you just want to train a model to play chess, which is not really a next token prediction game. It's actually a research game. But even with just training, uh, if you just want to train a model to predict the next token for playing chess, you require around 200 million parameters and 1 million games. And with that scaling of data, as well as with that scaling of model parameters, you can already achieve grandmaster level of chess play. And this is like a paper from DeepMind. So the scaling law requires us to push the model parameters higher and higher. And this is what is driving the growth of how many GPUs we need to train, how much compute we need to train this, as well as what is required on the edge devices to be able to train and infer this, because it's always about how do we get that much memory on the edge devices.
Sharad, given that, when you look at now multimodal Gen AI, when we pull together video, images, text, music, whatever the modes may be, how do those trends impact deployment? Does that just make it even more complex?
You're absolutely right, Tim. As we go through multimodal, we need to understand different modalities. Like modality typically refers to a way the input and output is being represented. So LLMs were initially started with the text representation, but now LLMs can support audio. You can directly have a conversation with LLM, which feels more real time. Video, where you can actually ask the language models, and there are no more language models, right, in that at this level, where they can understand the image and the what modification that needs to happen to the images as well. So why multimodality is important, right? Like if I want to answer that, I had to like take a step back and see what used to happen 2 to 3 years back. Because even then we used to have like audio processing capability. But for that to work, you had to have enough context of the audio, and then we used to parse the audio. Then we used to go through the language processing model, for example, to do a translation. Um, the multimodality takes that adapter out. Like you have adapter which takes from audio to language. That adapter is no longer there, and the models can natively understand what it means to have a voice. So, so similarly for images, like models can natively understand by using some sort of embedding representation. They can natively understand what it means to represent like a tree in an image, and that is very powerful. Like you current capabilities of what GenAI is allowing, we can really have a conversation without feeling the latency. You still have the network latency, but you can still interrupt the model, and the model will actually understand your intent. And the model might even interrupt you in future, but that's something different, right? And for the images, for example, we use cross attention layers, like as one of the example, right? Like uh, in a case where you want the original text processing to be the same, you can insert additional layers for image processing and create more complex behavior of the model to be able to generate or process images. And all this is resulting in is larger and larger sizes of the models. You can have different adapters, like for image processing versus video processing. You can also train the models which actually have larger context ability. So the image processing models can actually be extended to keep longer and longer context and have similar characters or similar background in the images through the video or through the video frame. And this is being used to be able to keep like the ability of LLMs to keep the context at the longer term has been used to like extend the GenAI capabilities predictably over the video frames. And this does create larger context. And even that context is a very memory intensive context. I would say that like this multimodal nature of the uh, Gen AI processing has become more and more memory intensive in terms of what needs to be stored and what needs to be fetched.
Sharad, given what you've talked about with all of these trends in Gen AI, what are some of the compelling applications you're seeing?
So I would like to categorize the applications into three different stages, and I think I pretty much copied this from Simon Wilson's blog. So I'm not saying that the industry is somewhat aligning to these three different stages
Okay.
of application. So the first one is human replacement, or you're creating almost an AGI, general intelligence. These
Right.
applications seems to be slightly away. We really not sure when we'll have a robust enough autonomous agent that we can be used in a real life to be able to practically hand off something like managing your bank account, or like
Okay.
even for example, like book me a flight ticket. Even simple example like that, handing it off completely to autonomous agent is still quite risky when it comes to money or any critical system. So
Exactly.
we do see some prototypes happening there, but not really something that is deployed at the uh, consumer level. Um, the second level of application, and this is more interesting to me personally, is supervised agents. And it has become much more interesting because these agents have now the interfaces to the agents or LLMs have now editing capabilities. You can just edit a small portion of a document, and you can keep the history. You can go back and forward in the history. And the whole idea behind supervised agents is you are going to give it a small task, and you are going to review the result that comes out of it.
Hmm.
And it's a way to use the LLM's capability in the most robust fashion, where you are reviewing everything. And for example, if you are doing something to code modification or like autonomous testing, even giving access to the agents to your screen and like let them understand the screen and play around with the screen for the testing. And that is actually quite interesting, quite useful. And I personally get most benefit using this way of using the Gen AI methods, right? And if you look at image generation, those are more like toys. Like this is like a subcategory of supervised agents. And these toys can be deployed even on edge devices because you can just change the image, and if you don't like it, you replace the image. And if you're not really cared about that much about the accuracy impact of the output, then deployment of these toys on the edge devices becomes more interesting part, right? Like then you're not
Hmm.
really looking for larger and larger models. You can trade off accuracy by quantizing the models, right? And third part or third subcategory, I would say, of the application is like COGS. And COGS is, or it's basically a tools. So unsupervised agents. So these tools can be very predictable output, but they do extremely small tasks. And Gen AI has become come to that level where it can do translation completely unsupervised. Like you don't really have to even look into if the translation is accurate or not. And even changing, like generating a voice, understanding voice. And if you use this capabilities of Gen AI, you can actually build pipelines. For example, understanding documents, trying to summarize the document. You can build a pipelines of these whole tools together and produce something interesting. And this is basically the multi-agent approach to solving complex problems. And as these tools become more and more predictable, the overall how many agents you can put in the loop, can you use a planner agent to be able to drive these agents, becomes a very useful approach to this. Some of these tools we already see on edge devices, right? Like for example,
Hmm.
automated translation. We already see that like small models can already translate live without need to the cloud. Or even understanding voice commands in vehicles. We don't have to depend on the connectivity to the cloud. So these are the set of applications are getting good tractions right now, and a lot of industry focus has been towards pushing these forwards.
Okay, great. Now, given all those implications, these applications, the size of the models, what are the challenges ahead from an AI hardware standpoint? What do we as an industry have to focus on, and what are those pain points?
So if we are looking into training of these models, we are talking about thousands of GPUs. Like the large language models requires like humongous amount of data because of the scaling law to be able to gain that intelligence. And we are looking into thousands of GPU being used. And to be able to keep the GPUs busy, you obviously have to manage the power and all the other things, but most importantly, the interconnect part. This interconnect is how we can actually train the same model across these machines, across these GPUs. And how do we manage that? How do we make sure that the utilization is always high enough? Uh, is going to be the challenge for training. Because training is not a problem of deployment, it's a problem of orchestration. How do you get the best out of the data center that you have in terms of like ingestion of the data set, as well as like parameter optimization and keeping like even think like fault tolerance is becomes important here because we are training across months. So uh, as the models become large and large, the cost of training the models are going through millions, like maybe even tens of millions. And that means that robustness of training and utilization of the underneath hardware becomes extremely important for from cost perspective, right? The other aspect of it is memory, right? So when when we need to store the models and at different accuracy level, we might have to store in floating point 32, floating point 16. And this is true for inference and training both. That when we need to store the models, we need to make sure that the model is available in low enough cost memory, or like, let me rephrase it as cost sensitive memory. So current trend is everything is going through HBM, right? We are pushing everything to HBM, and um, that is because the current compute architecture requires high bandwidth. But LLMs especially at the data center, don't necessarily have to be consuming that much bandwidth. The reason we use HBM is not because of the storage, but because of the bandwidth, and that's the limitation of the compute architecture. So we need to find better compute architectures and better memory alternatives to that high bandwidth, because purely because of cost perspective, because otherwise um, we are paying 10x for just the storage of the memory. And this this is true not just for the parameter storage. As we see LLMs grow, as we see that like, hey, even open source model is supporting 128,000 token context, right? 128,000 token context is almost equivalent to 100,000 words. So as the LLMs can understand 100,000 words or generate 100,000 words, the context for that spans up to 10 gigabyte per request. Now that also needs to be stored during the inference. And this is something that we don't really see unless you are trying to deploy the model. So during the model deployment, it's not just the weights that are important to store. Like even if you store, like, weights don't change. Weights are fixed for the foundational models, right? Weights are fixed. But the context that you need to store changes based on how many requests that you get. And that scalability is based on the incoming user request. And so it is very critical that we have low cost memory alternatives to be able to support that, or be able to advance the need of the data center, uh, or scale the need for the data center to scale the deployments to multiple users and maybe thousands of users.
So Sharad, as an architect, if you're building an AI inference system, what's your top priority? Is it capacity to hold the bigger models, or is it bandwidth? Because you got to move parameters, models, requests on and off, and in and out of memory more quickly.
Um, so this is a very difficult question. If I have to make a call as a hardware architect, I would try to answer this based on a workload, right? So
Right.
if we are looking into training, training requires parameters to be updated, parameters to be modified, and these parameters are quite large part of the training workload. Like it's not the
Yes.
activations, it's just the parameters. And so these movements and these interconnects requirements are extremely high during training, and which means the bandwidth will become a critical factor there if I need to choose that. But if I am looking into the inference market, it turns out that the total capacity of the memory is very critical, and it's not just the total capacity, but the capacity at the cost, because
Right.
inference is much more cost sensitive, and we need to be able to scale the inference, because if you have invested so much money into training a model, we have to get the return of that investment. So the inference is actually need to be scaled to many more devices or many more applications to be able to get that return. And we would see this flip happening in the recent years, and which means the cost of the memory at the capacity or capacity per cost becomes a critical factor for the deployment. So, like just to summarize, for training, it is utilization per bandwidth or
Right.
bandwidth per utilization. And for inference, it would be maybe cost per storage or like storage at given cost, right? And that's pretty much would drive how the hardware architectures are looking into the memories.
Okay. Very good. Sharad, how can people learn more about Expedera?
Um, Please visit our website at expedera.com and feel free to also reach out to me on LinkedIn. You can add me on LinkedIn or send a message on LinkedIn, and I would be sure to respond.
Wonderful. Thank you so much for your time, Sharad. And thank you, everybody who joined us today. We will see you back here on Ask the Experts real soon.
Thanks for having me. Thank you.